have to worry about nothing. 'Cause we got the fire, and we
Good morning, good afternoon, good evening. Whatever the case may be, we are back and better than ever. And thank you, Ellie. We certainly do not have to worry about nothing because we are deep into calculus. We have lit that fire and we are going to burn, burn, burn. As always, thank you, Sir Isaac Newton. Thank you, Gottfried Wilhelm Leibniz. Let's get to it, shall we? Let's find the area between two functions. Here we only have one function, just to sort of start us off. We have the function y equals f of x, do we not? We do. And let's just say we wanted to find the area under the curve bounded by a, b, and the x-axis. And we already know that that would be the integral from a to b of f of x dx. Okay? But what we haven't ever really thought about is the x-axis also has equation y equals 0. And just put that in your back pocket. We'll talk more about that when we do the example. Okay? But let's say that there was another curve. Okay, like maybe right here, so to speak. There it is. It magically appears, and I need to do a little bit of work to fill it in there. But let's say that black curve there is part of another curve. That doesn't look very curvy, but build a bridge and get over it. And we'll call that curve g of x. Okay, and I wanted to find the area right in here between f of x, g of x, and of course a and b. How would I go about doing that? Well, if I had a pair of scissors to find this area here, if I wanted to like actually physically pick it up and take it away, I could just use scissors and cut this out right here, couldn't I? I could cut it out. Well, what would that look like? I could cut it out and away it would go, right? And I'm left with the area in question. Yes, I'm left with the area in question. Well, the mathematical equivalent to cutting something out is subtraction. So let me put that curve back in there so we can kind of see the full thing. The area between the two curves, and I will call that area A, area is equal to the integral from A to B, and that's actually where the two curves intersect. For my example, it just happens to be on the x-axis, but it doesn't have to be on the x-axis, of f of x, the function on top, minus g of x, the function on the bottom, dx. And with a better picture and maybe a better look on this page from the book, we have a nice little picture here, and notice that the A and B, those points are not on the x-axis, or these points don't lie on the x-axis where they intersect, but this is the point x equals A and the point x equals B. We take the upper function minus the lower function, and they have some nice notation here where they say, okay, let's just call the function on top y sub u, right, that bounds on the top bound of the region in question, and the one below it we'll call y sub L for lower. Looks kind of odd there because visually right now the L is above the U, but with the bound, the upper is above the region and the lower is below the region, and of course it closes it in. So all we have to do is integrate the difference. That's all we have to do. And right here I have sort of X'd off a nice little proof that you can pause and look through if you want. But we're going to get right to the example, shall we? So let's use the integral from a to b of y equals u of y sub u minus y sub L dx, the upper curve minus the lower curve, upper function minus lower function, however you want to think about it, to find the area bounded by the x-axis and y equals x squared minus 2x. So let's just, put our thinking caps on here. This is a parabola, and we know that it opens upwards. So if we're going to be bound by the x-axis, then we need to find the x-intercepts. And we do that by setting the function equal to 0. So x squared minus 2x equal to 0. Factor out an x, x times x minus 2 equals 0. So that means x equals 0 and x equals 2. So I have my intercepts here, and let's call this 2 right here. Okay, and we know it's a parabola, and we know it opens upwards, so the only possibility is for this region to dip below the x-axis. Okay, now remember, I said, and of course I know you know this because you guys are awesome, the equation of the x-axis is y equals 0. Now, from previous experience, before I say that, we are looking for this area here. It's bounded by the x-axis and the curve y equals x squared minus 2x. Okay? Now, we already know that we could find this area by integrating from 0 to 2 of f of x, which is x squared minus 2x, dx, that is a horrible looking 2, x squared minus 2x, and negating it to compensate for it being under the x-axis because the integral will come out negative. But we know area can't be negative, okay, so we compensate for that. But using y sub u minus y sub l, we don't have to worry about that negative. It really is your choice. It doesn't matter for this particular kind of example. It matters very much when we're not dealing with the x-axis, and you'll see that in just a second. But for this bound, y equals 0 is the upper curve, and y equals x squared minus 2x is the lower curve, because that's the upper and lower parts of the boundary. So I could write this as area equals the integral of 0 minus, don't forget the parentheses, x squared minus 2x dx. And with a little bit of algebra, that's equal to the integral of negative x squared plus 2x dx. And I forgot to put the bounds on there from 0 to 2. Shame on me. And so that would equal negative x cubed over 3 plus integral of 2x is going to be 2x squared divided by 2, or simply x squared, evaluated from 0 to 2, which would be equal to negative 2 cubed over 3 plus 2 squared minus, parentheses, replacing 0, we're going to get 0. I won't do the arithmetic. I will tell you that that area is equal to 4/3 square units. Okay, next example. Find the area of the region enclosed by y equals x plus 2 and y equals x squared plus x minus 2. Now this is a line, so it's always nice to sketch if you're a little confused, especially if you're just starting out. And y equals x plus 2 could look something like that. Y-intercept is 2. So this is y equals x plus 2. Okay. So if it's bounded by these two curves, I have to see where these two curves intersect to get my bounds. So x plus 2, I have to set them equal to each other to see where their x coordinates are equal. Equal to x squared plus x minus 2. X's go away because they're the same. So I get what? Let's see. 0 equals x squared minus 4. And solving that, x equals plus or minus 2. Okay, that happens to be an x-intercept, doesn't it? Right here, or yeah, an x-intercept. So that's negative 2 right there, and so by symmetry, that puts 2 about right there, which means that x squared plus x minus 2 intersects y equals x plus 2 right here. Okay. And from there, you can get a decent sketch of the parabola. You know it opens upwards, so it's going to look something like that. Okay? And from the sketch, or if you know your functions well enough, you can tell which is the upper curve and which is the lower curve. So we are finding the area bounded by these two curves, and there they go, right? Well, which is the upper curve? It's this one, x plus 2, because it is the curve on top. And this is the curve that bounds the bottom of the region here. So the area is going to be equal to the integral of the upper curve, x plus 2, minus the lower curve, x squared plus x minus 2 dx. And the bounds are where the curves intersect, from -2 to 2. So this would equal the integral from -2 to 2 of x plus 2 minus x squared minus x. Let's see, that's going to be plus 2 dx. Clean it up a little more before I integrate. -2 to 2. Let's see, x minus x gone. 2 plus 2, 4. So that's going to be the integral of negative x squared plus 4 dx. And so that will equal negative x cubed over 3 plus 4x, evaluated from -2 to 2. So I would substitute in positive 2 and then subtract, substituting in -2, the result of that. And to save time and without showing you, I will tell you that we end up with, let's see, 32 thirds square units. 32 thirds square units, which is equivalent, obviously, to 10 2/3 square units. Check that with your calculator. Go ahead, check it out, see what we get. And one final example, find the total area of the regions contained by y equals f of x and the x-axis for this function. Okay, so let's get an x-axis, an xy axis system real quick. And anytime we're dealing with the x-axis, we want to find the x-intercepts. And we have a cubic, so we know that it's going to be generally in this shape. I don't know why that just happened, but something like that. Okay, because the coefficient of cubed is positive. If it were negative, then it would look like that with this first part dipping downwards. All right, so let's set this equal to 0 to find our intercepts. X cubed plus 2x squared minus 3x is equal to 0. I can factor out an x. X times x squared plus 2x minus 3 equals 0. X times x plus 3 times x minus 1 equals 0. So I get x equals 0, x equals -3, and x equals 1. And that is enough. That is really all we need. -3, 0, and 1. And if you know your functions, then you know that it's going to look, this curve is going to look something like this because of the positive coefficient of the cube term. If you're not sure, you could just use a test point like -2 here and see what the value is. So we are looking for this area here, and we are looking for this area here. Okay? So all we would have to do now is take upper minus lower. So the integral from, now we're going to have to do two integrals since we're over the x-axis and then we go below the x-axis. So we're going to go from -3 to 0 of x cubed plus 2x squared minus 3x dx minus the integral, this one right here, and minus, it's below the x-axis, 0 to 1 of the same integral, x cubed plus 2x squared minus 3x dx. Okay? And if we integrate that, what do we get? X to the 4th over 4 plus 2/3 x cubed minus 3x squared over 2. Evaluated. Sorry, I'm running into the integral here, so I'm going to go pink in case I have to overwrite something. -3 to 0 minus, okay, and I'll put a parentheses there. It's the same integration, x to the 4th over 4 plus 2/3 x cubed minus 3/2 x squared, evaluated from 0 to 1. And you have a lot of arithmetic, that's a bad 3, a lot of arithmetic to do there, but what you end up with is 11 1/4 For this guy, minus a negative 712. So you just have to trust me on this one. And we get a final area of 11 5/6 square units. Check it on your calculator. That is it for this video. I hope you enjoyed it as much as I did. I am out.